1, correct? And the other one should fall out as a whole number as well. And dividing that through, I'm getting 2.99. Is 2.99 a whole number? No. Is it perilously close to a whole number? Yeah. What would that round to? 3. And so basically we've got a 1-to-3 ratio. 1 carbon for every 3 hydrogens. And so you would write that as a formula being 1 carbon and 3 hydrogens. That's our empirical formula. We've done some rounding here. Because it's not going to fall out exactly on an integer, but it should fall out extremely close. When you're doing empirical formula calculations, you've got extremely narrow rounding limits, and that is you have to be within 0.05 of a whole number to round to that number. So for example, 2.99 is within 0.05 of 3, so we're safe rounding to 3. If this had been 2.96, we're still within 0.05 of a whole number, that would round to 3. But if we had 2.90, that's not 3. That's not close enough to 3 to be roundable to 3. Very narrow rounding limits. I'll show you what to do with that in just a moment. But for now, one major problem people have with empirical formulas is they round too much. So just know it's got to be extremely close to be roundable. Question about getting CH3 as the empirical formula. We didn't do a whole lot of math over there. We divided by molar mass, and then we divided the moles by whichever one was lesser. And that fell out to be the numbers that go as subscripts in your formula. Is there a question about that? That CH3 is your empirical formula. As far as molecular formula goes, maybe it's really CH3, or it could be this, or it could be this, or it could be this, or it could be several other things. This is multiplying the subscripts by 2, this is multiplying those subscripts by 3, by 4, and etc. All of these are a list of possibilities. Essentially, empirical formula is giving you a list of possibilities of who that formula could be. But just empirical formula calculation alone is not enough to do an actual ID on it. But it gets you close. It gets you to a list of possibilities. Is there a question with that? All right. Problem number 11. This time we've got carbon, hydrogen, and oxygen. So generically, it's this. What we're given is not actual masses for the elements that are present. We're given percent composition data. But that's okay because we know how percents work. Percents have to add up to 100, correct? And since these are percents based on mass, we can treat them as mass. If you're told that this compound is 48.64% carbon, then that means if you had 100 grams of the compound, 48.64 of those grams would be carbon grams, right? So take that as carbon grams. And that's 43.20 oxygen grams, and that's however much is left as hydrogen grams. 8.16. The problem doesn't tell you that it's 8.16% hydrogen, but that's kind of implied because your percents have to add up to 100. So we're treating those as if they were actual grams, and we convert each of those into moles. This is what I'm getting for mole amounts. Nothing but molar mass conversion so far. Question there. All right. Next thing to do is to make whole numbers out of it. Which element do we have the fewer moles of? Oxygen. So we divide them each by moles oxygen. Purposely doing that to make the oxygen fall out as 1. And anticipating that the others will fall out as whole numbers as well. But they don't. I'm getting 1.5, 1, and 3. 1.5 is obviously not a whole number, and it's nowhere close enough to be roundable to a whole number. But that is the proper ratio. Question about getting that ratio. All right. So if we can't round that 1.5 to a whole number, then we need to start thinking multiples. What can you multiply it by to get a whole number? 2. If you multiply this moles carbon by a factor of 2, then it becomes a whole number, correct? But you can't multiply the carbon by 2 without multiplying the others by 2, otherwise you lose your ratio. 1.5 to 1 to 3 is the correct ratio. But once you multiply that up, it becomes a 3 to 2 to 6 ratio, and then the carbon would be subscript 3, the oxygen would be a subscript 2, and the hydrogen would be a subscript 6. Notice there's nobody in that formula that really truly has a subscript of 1. And sometimes that happens. And if you're dealing with something like that, then you're going to have one of these situations where you have to seek out a multiple. Question with that. That's your empirical formula.
You're adding 2 in there? Why'd you add 2 again?
Not adding 2, multiplying by 2. What we were doing is making sure that the carbon one came out as a whole number.
Oh.
But you can't just multiply the carbon one or you lose your ratio. All right. Now, the next part of this problem is wanting you to go from the empirical formula to the actual molecular formula. And the extra piece of information it gives you is molar mass. It tells you that the actual molar mass of the compound is 222.2 grams per mole. what we need to do is figure out the molar mass of this. Oops, it has 3 carbons in it. It has 2 oxygens, 6 hydrogens. I'm getting 74.079 grams per mole as the molar mass of the empirical formula. Adding up everything in the empirical formula gives me 74, not 222. So apparently C3O2H6 is not the real actual molecule, or it would have weighed 222, right? But your empirical formula, or let me say it this way, the actual molecular formula is either the same as the empirical or it's some multiple of the empirical, meaning its molar mass is going to be some multiple of that empirical mass. And so if we divide this, this is the actual molar mass divided by the empirical molar mass. Then that's going to tell us how many times heavier the real molecule is compared to that formula. Because if the real molecule is twice as heavy as the empirical, then it must have twice as many atoms. Or if it's 3 times as heavy, it'd have 3 times as many atoms. 222.2 divided by 74.079 is pretty much 3. I got 2.9995, etc., etc., etc. This is telling you that the real molecule is 3 times larger than the empirical. If it's 3 times heavier, it's 3 times bigger. That means 3 times as many of the elements. So how many carbons are there really? And oxygens and hydrogens. 18. That's your real formula. That's the real molecule. Taking your percent data and converting that into an empirical formula gives you a list of possibilities. An empirical formula is a dead end unless you know the actual molar mass. You've got to know the molar mass to take that extra step from empirical formula to molecular formula. Question?